Hi everyone, my name is Kiana Montest. I'm from Samtec. In today's topic, we're going to be talking about using an array when a standard PCB connector won't do. The design solution is driven by the development of RF SoC devices, which is a single chip baseband system on chip product with integrated data converters in front-end system, which are now being deployed in various applications such as 5G, 6G, phase array radar, SATCOM, FPGA, test and measurement. This development challenges our traditional approach of using RF connectors, such as threaded RF connectors, compression mount, or even our ganged RF connectors. The reason being is that these RF SoC devices are now requiring dozens, if not hundreds, of RF signal chains. And so having like an X amount of RF connectors in array form factor can be prone to connector misalignment. It could take up PCB space, and of course would not be cost effective. The approach that we're considering in this case is using an existing interconnect that was originally designed and developed for high-speed digital signaling and using it and adapting it into RF signal applications. This design solution is what we're calling our Samtec analog over array technology, because analog signaling is not discretized. It is important that we have high isolation, and with an array connector being open pin filled, we're able to achieve that. So here are just a couple of array connectors that we offer here at Samtec. It could vary to the number of pins, your pitches, and performance essentially. So there are benefits of using high-density array connectors in terms of RF analogs applications. First of all, flexibility. Again, like I said, this has been already proven for digital signaling, and so having to send analog signals into our array connectors would be beneficial for your application. So it could essentially send signal, power, and analog signals simultaneously. Second benefit is high density. Again, kind of goes hand in hand with that. We're able to reduce the number of connectors in the system by being able to send digital power and analog signal in one connector. Of course, cost, the fewer connectors that you have in your system, the less you would spend on connectors. So this is what Samtec analog array technology looks like. Currently, the open pin-filled array, we have our digital differential pairs, single-ended, power, and now with enhanced analog array technology, we're adding analog differential pair and single-ended into the mix. So how can an engineer implement analog array technology? So before that, as a benchmark, use AMD Zenk UltraScale Plus RFSoC key design specification throughout our optimization of our connectors. In this case, the design specification calls out for return loss of 10 dB up to 7.125 gigahertz. And then for your crosstalk, we have 63 dBc up to 7.125 gigahertz as well. And this is for both ADC and DAC. So the first key design choices that I'm going to be talking about is the 115 ohm to 100 ohm trace transition approach. Just want to point out the connector that we're using here is C-Ray. It's one of our popular connector that's being used all over, different applications. The C-Ray in this case has 127 millimeter pitch. What's happening here is because the impedance from the PCB transition to the connector is really capacitive, we're kind of introducing inductance over it. So that's why you're seeing it in the impedance plot. We kind of pull that capacitance, so kind of balance it each other out. So in this case, what we did is to taper our trace, in this case, based on our stack up from 4.5 mil to a 3.5 mil trace width. Like I said, we purposely increased impedance to 115 ohm to compensate capacitance in the capacitive region of the PCB transition into our connector. So the second key design choices that we kind of looked at is what the optimal pin orientation is. So C-Ray has a symmetrical pitch, so 1.27 millimeter, row to row or in column to in column. However, if you look at the pin orientation or the pin geometrical structure, you would see that there is difference. So what we have here is an in-row pair, which is edge coupling between signal pair, and then the second one is our in-column pair, broadside coupling between signal pair. So what I have here is just a result of return loss. I have the two different pin orientation with the 115 ohm or not having that 150 ohm trace differentiation that we just looked at in the past few slides. Broadside coupling with the 115 ohm trace transition, we're able to get a pretty decent return loss up to 20 dB, 8 gigahertz. So that means only 1% of the signal is getting reflected back. And then we don't have any resonance compared to the rest of our curves. So again, like I mentioned in the beginning of my presentation, with analog signaling, high isolation is an important part that you need to consider. And so the most obvious way to mitigate crosstalk is to configure your pins. As you can see, we surrounded our signal, differential signal in this case, with a lot of ground pins to mitigate that crosstalk. Another way to mitigate crosstalk is surrounding our signals with ground vias to kind of shield that energy that could propagate to your other signals, which is causing your crosstalk. And as you can see here at our next and vext plot, we're able to achieve up to about 70 dB at 8 gigahertz. We have pretty good margin based on the key design specification that AMD had stated. So we've been looking at performance of our connector with a breakout region. Now we're going to look at the channel performance. So what we did here is just adding losses and placing the connector at different locations within the trace. So essentially you have one connector in the middle. On the other side, we have like constant value of 1 inch of trace. And on the other side, we're going to vary the length by 2, 4, and 8 inches. So what I have here is our return loss and insertion loss results. And as we can observe, they have similar behavior from 0 to 10 gigahertz. But as you go to higher frequency, the difference is pretty apparent. I want to point out that at 20 dB, essentially, you only have 1% of energy getting reflected back. And of course, your insertion loss, as you go in longer traces, we get more lossy. So for our power sum topology, again, we have one victim here surrounded by 5 aggressors. And as you can see, they are pretty much the same behavior up to about 10 gigahertz. And as you go in higher frequency, you see those differences. We achieve that specification stated by AMD. So key takeaways, like I said, array connectors can have its benefits. Flexibility, density, and cost could provide good solution for your RF analog application. And by designing the launch, you're able to, again, support those applications that you might need. So here are all the available technical support that if you want to learn more about analog over array, we have e-brochure, white papers, of course, characterization reports, and we also offer evaluation kits. If you guys wanted to test that in your lab, we offer that. Thank you all for coming. If you have any more questions or you want to talk, you can contact us at samtec.com. Thank you.